Nat 405 Physics, Newton's second law. The key areas we will cover today are the relationship between force, mass and acceleration, the equation for Newton's second law, and using this equation to calculate force, mass or acceleration. Newton's laws. From practical work or research, find the relationship between the variables force, mass and acceleration. It can be shown that the acceleration of an object will increase when the force acting on it increases, assuming no change in mass, and the acceleration of an object will decrease when the mass of the object increases, assuming no change in force. Newton carried out practical work and research on this relationship. This work helped to form his second law of motion, which is normally written as the following equation: F equals ma, where F is the unbalanced force measured in newtons, m is the mass in kilograms, and a is the acceleration in meters per second, or meters per second squared. This equation can also be written as a triangle. If we want to find the force, we would cover up the F and find that force equals mass times acceleration. If we want to find the mass, we cover up the m and find out that mass equals force divided by acceleration. And if we want to calculate A, we find out that A equals F over m. Example 1. An unbalanced force acts on a mass of 15 kilograms, which makes it accelerate at 5 meters per second squared. Calculate the unbalanced force acting on the mass. This is a simple equation question, so what we want to do is first write down what we know and what we want to work out. So the symbols in our equation are F, m and A. Looking at our question, we can see that we've got a mass of 15 kilograms, and we have an acceleration of 5 meters per second squared. We want to work out the unbalanced force acting on the mass. Now we can use our equation, F equals ma, and put in our numbers. So our force equals 15 times by 5, and so we get to a final answer of 75, and that's measured in newtons as its force. Example 2. A sledge is being pulled by an unbalanced force of 90 newtons. The sledge accelerates at 4.5 meters per second squared. Calculate the mass of the sledge. Again, we want to write down our values. We are given a force. We can see it just there, that's 90 newtons, and we are given an acceleration, which is 4.5 meters per second squared, so we can fill both of these numbers in. We want to work out the mass of the sledge, so that's where we put our question mark, and now we can use our equation. Force equals mass times acceleration. We can pop our numbers in, so 90 equals m times by 4.5, and now we need to rearrange this. This gives us mass equals 90 divided by 4.5. 90 divided by 4.5 is equal to 20, so that's our final answer. The mass is 20, and that's measured in kilograms. Remember, mass is always in kilograms. Example 3. The unbalanced force acting on a car is 1,900 newtons. The car has a mass of 1,000 kilograms. Calculate the acceleration of the car. As always, F, m and a down the left-hand side. We have a force of 1,900 newtons, and we have a mass of 1,000 kilograms, and we want to work out our acceleration. So we use our equation, force equals mass times by acceleration, and pop our numbers in. So 1,900 equals 1,000 times by a. We now rearrange this, so our acceleration is equal to 1,900 divided by 1,000. Therefore, our acceleration is equal to 1.9, and remember our units, they are meters per second squared. What you can do now for extra practice is copy and complete the following table. Pause here to give yourself enough time for this. You can now check your answers to the previous table. We have a second part to our calculations now. The first example for this is our box X accelerates at 2.5 meters per second squared, and we want to calculate the mass of box X. However, we are not just given one number for the force, we are given two numbers, 10 newtons and 25 newtons. We can see these are acting in opposite directions, but they're not the same number, so we've not got balanced forces, we have an unbalanced force, and that's what we want to find out first. So our unbalanced force, which I will label F with a subscript of UN for unbalanced, is going to be equal to our force forwards in the forwards direction, which I'm taking as to be this direction. And we're going to take away our force going backwards. What this becomes is our unbalanced force is 25 take away 10, and so overall our unbalanced force is equal to 15 newtons. Having a look at the question, we can see we have an acceleration and we want to calculate the mass. So our mass has a question mark next to it and our acceleration is 2.5 meters per second squared. Now we can use our equation just like before, F equals ma, and pop our numbers in. So we use 15 for our unbalanced force, which is equal to our mass times by 2.5. Rearranging this, our mass is equal to 15 divided by 2.5, and so as our final answer, we do 15 divided by 2.5, which is equal to 6 kilograms. Example 2. Box Y has a mass of 5 kilograms. Calculate the acceleration of box Y. Again, we're not just given one force, we are given multiple. So having a little look, we have 6 newtons and 6 newtons pointing to the left, and 28 newtons pointing to the right. So just like before, we first want to find the unbalanced force. And that's going to be equal to our force forwards minus our force backwards. We can see our force forwards is 28, and our total force backwards, we have to add these two sixes together because they're pointing in the same direction. We know that 6 plus 6 is going to be equal to 12 newtons. So our backwards force is 12. 28 take away 12 is equal to 16 newtons. So that's our overall unbalanced force. We have a mass given in the question, that's 5 kilograms. And our acceleration is what we want to calculate. Now we can use our equation, force equals mass times acceleration, and pop our numbers in. So 16 equals 5 times a. Rearrange this, it gives our acceleration is equal to 16 divided by 5, and this gives us a final answer of our acceleration equals 3.2 meters per second squared. Example 3. A 500-gram toy car accelerates at 3 meters per second squared when the engine force is 2 newtons. Part A. Calculate the unbalanced force acting on the toy car, and Part B. Calculate the frictional force acting on the toy car. This is different from our previous two examples because we're actually given one of the forces, but this is not the overall unbalanced force. This is what they want us to calculate first. So for Part A, using our equation, F, M, and A, we want to calculate our unbalanced force. We are given a mass, up at the top in the question, of 500 grams, and an acceleration of 3 meters per second squared. Before we use the equation, we need to notice that the mass should be in kilograms. So 500 grams in kilograms is 0.5 kilograms. Now we can use our equation, F equals ma, to calculate our force. So our force is equal to 0.5 multiplied by 3, which gives us a force of 1.5 newtons. Now we look at part B. Calculate the frictional force acting on the toy car. Looking at our diagram, we know that the engine force is pushing the car forwards and the frictional force is acting backwards against the car. Similar to previous questions, we can say that the unbalanced force is equal to the force forwards minus the force backwards. We already have the unbalanced force this time, that's 1.5. Our force forwards is the engine force. We can see this is given in the question, that's 2 newtons. and our force backwards is what we want to calculate. That's our frictional force. So 1.5 equals 2 minus our force backwards. Now we can rearrange this, and so our force backwards is going to equal 2 minus 1.5, and so our frictional force is equal to 0.5 newtons. Example 4. A physics trolley with a mass of 0.4 kilograms accelerates at 2.5 meters per second squared. The force of friction acting on the trolley is 5 newtons. Part A. Calculate the unbalanced force acting on the trolley, and Part B. Calculate the force pushing the trolley forwards. Let's have a look at the question and see what we have. We have a mass, and we have an acceleration. We also have a force of friction acting on the trolley. So this is going to be similar to the last question, because our first part is asking us to calculate the unbalanced force. Because we have a mass and an acceleration, we can straight away use our equation. So F, M, and A. Our force has the question mark next to it, our mass is 0.4 kilograms, and our acceleration is 2.5 meters per second squared. Popping these numbers into our equation, we can see F equals ma first, then F equals 0.4 times by 2.5. Popping that into a calculator, we get to 1. So our force is 1 Newton. For part B, we want to calculate the force pushing the trolley forwards. Similar to previous questions, we can write out that our unbalanced force equals the force forwards minus the force backwards. We've just calculated our unbalanced force, that was equal to 1. Our force forwards is the force pushing the trolley, so that's what we need to work out. And our force backwards is given in the question. This was that 5 newtons, which was the force of friction acting on the trolley. So 1 equals our force forwards minus 5. Rearranging this, our force forwards equals 1 plus 5, and so the force pushing the trolley forwards is 6 newtons. For extra practice, you can copy and complete the following table. Pause now to give yourself enough time for this. Now you can check your answers. Now we have a third part to our calculations. Vector quantities, like force, can be represented by a straight line which ends with an arrowhead. 2 or more vectors can be combined to give a single vector, known as the resultant vector. This is very similar to when we looked at displacement and distance. If you need a recap on that, you can go back to a previous lesson and watch it over. The resultant vector must be stated with a magnitude and a direction. When solving vector problems, the individual vectors must be combined using the tip-to-tail method. This method can be used for any vector quantity, for example, velocity. In this case, we will be using it for force. Example 1. 2 forces act on an object as shown. This is down at the bottom left. We have 120 newtons acting to the north of the object and 50 newtons acting to the east of the object. Part A. Calculate the magnitude of the resultant force, and Part B. Calculate the direction in which the resultant force will act. You can see across at the right-hand side just here we have a little compass. When we draw our diagrams, we always make sure north is pointing upwards on our page. Let's go for Part A first. Calculate the magnitude of the resultant force. Before we can do this, we can't just put a dotted line on this diagram. That doesn't work. We know we need to draw our arrows tip to tail. So first of all, let's take the larger number, our 120 newtons. We can draw this from our start point, pointing straight up. That's our 120 newtons. Now the 50 newtons is also acting on the object, but because we have to draw the arrows tip to tail, we start at the tip of the previous arrow and draw our 50 newton arrow to the right. Now that we have our arrows tip to tail, we can draw on where our resultant force is going to be. That's this red line I'm drawing in here. Remembering back to our recap on Pythagoras and trigonometry, we know that we can use Pythagoras to work out the length of this resultant force. I'm going to label this F to make things easier, so we can say that F squared is equal to 50 squared plus 120 squared. 50 squared plus 120 squared is equal to 16,900 altogether. So our F squared equals 16,900. And we now want to take the square root of this to get to our resultant force. So the magnitude of our resultant force is equal to 130 newtons. For part B, we need to calculate the direction in which the resultant force will act. To do this, we want to put our angle symbol in here. So we always do this from the start point. Our angle theta is going to be just here. We want to use trigonometry to work this angle out. And again, if you need a recap on this, you can go back to one of the previous lessons where we recapped trigonometry. First, let's label our sides. So we've got the hypotenuse, which is our resultant force. We've got the opposite, which is 50 newtons, and we have the adjacent, which is the 120 newtons. Now, writing out SOHCAHTOA, let's tick which ones were given in the question, which was the opposite and the adjacent. So we're going to be using tan. Tan of our angle is equal to opposite over adjacent. So filling in our numbers, tan of our angle is equal to 50 over 120. We now need to rearrange this to get just the angle. So that's going to be equal to the inverse of tan of 50 over 120. Remember, to get to the inverse of tan, you want to press Shift on your calculator and press the tan button, and then put 50 over 120 in the brackets. This gets us an angle of 22.6198 and so on, and we can round this to 23 degrees. However, we always need to give this direction as a bearing from north. In this case, this is quite easy because our initial direction was north. So we can give this as a bearing, and that means it has to have a 0 in front of it. So our bearing or angle is 0, 2, 3. So the final answer of the resultant force here, including both the magnitude and the direction, would be 130 newtons at a bearing of 0, 2, 3. Example 2. An aircraft's engines are producing a force of 2.2 times 10 to the 4 newtons due west. It then encounters a side wind which is blowing due south at 1.6 times 10 to the power 4 newtons. We can see a diagram of this here on the left-hand side. Calculate the resultant force on the aircraft. The last question asked us to calculate the magnitude of resultant force and then the angle, whereas this question wants us just to calculate the resultant force, which means we need both a magnitude and a direction. So first of all, what we need to do is calculate the magnitude of this force, but we can't do that straight away. First, we need to draw our arrows tip to tail. So we have the 2.2 times 10 to the 4 newtons pointing west, and then starting at our arrowhead pointing down south, we have 1.6 times 10 to the power of 4 newtons. We can then draw our resultant force on, that's the arrow in red here, and I'm going to label that F. We can calculate the resultant force using Pythagoras. So we know Pythagoras is the hypotenuse squared equals the addition of our other two sides squared. So F squared equals 2.2 times 10 to the power of 4 all squared, remember your brackets, plus 1.6 times 10 to the power of 4 all squared. So our F squared is equal to 7.4 times 10 to the power of 8. And square rooting that, we get an answer of 27,202.941, etc. But having a look at the question, our two numbers are given as two significant figures with times 10 to the power of 4 at the end. So we can write our resultant force in that same format. Therefore, our force is 2.7 times 10 to the power of 4 newtons. So we have our magnitude now. Now what we need to have a look at is the angle. Looking at our diagram, from our start point, this is where our angle is going to be. So we need to use trigonometry to work this out. Writing down SOHCAHTOA, we want to tick the numbers we've been given in the question. So we've been given, let's label these first, we've got the hypotenuse, we've got the opposite, and we've got the adjacent. We've been given the opposite and the adjacent, so we're using tan again. Tan of our angle equals opposite over adjacent. Filling in our numbers, we have tan of our angle equals 1.6 times 10 to the power of 4 divided by 2.2 times 10 to the power of 4. And then we need to rearrange this. Theta equals the inverse of tan of 1.6 times 10 to the 4 divided by 2.2 times 10 to the 4. We want to put this whole thing into our calculator. And what I get just there is an angle of 36. That's 0.027 and so on, but we want to round this to a whole number, so 36 degrees. Remember, just like the last question, we want to show this bearing, or show this angle as a bearing from north. I'm going to draw on our little compass just here. North is pointing up the way, but our angle looks like this, doesn't it? So what we want to do is take the bearing from north. I'm going to draw another little diagram showing this. This is our north. This is our angle just here. I'll put a dotted line showing this side of it. So we want this angle, whereas we currently have this angle. The angle 3/4 of the way around the circle to the dotted line just here would be 260. So what we can do is we can take 260. Oh, I'm wrong saying 260, aren't I? 270 even. 270, take away our angle, which is 36. And 270 take away 36 is equal to 234. So that would be our bearing from north. I'm going to show that again in another colour. Our bearing all the way around here to the dotted line is 270. That's 3/4 of the circle, 3/4 of 260. What we've done is we've done this 270 minus the 36, which is the angle in just here, and that gives us 234. Therefore, we can quote our final resultant force as 2.7 times 10 to the power of 4 newtons at a bearing of 234. That's our final answer.